Thank you everyone for attending this presentation on the topic of emulsion formulation and stability analysis. We'll be talking about emulsions, formulations, and also probably more focus on the analytical techniques that help us predict and determine stability of emulsions, including the Nicomp DLS system that we'll be using to measure the mean size of emulsion distributions, the AccuSizer, specifically the AccuSizer APS, which is the instrument we will be using to measure the tails of the distributions, and a direct measurement of stability is the Formulation Turbiscan. A quick outline of what we'll be discussing today is we'll be looking at emulsion formulations, the surfactant choice, emulsion stability, analytical techniques, the ones I just mentioned, DLS, Zeta potential, the Turbiscan, and the AccuSizer. And we'll be talking about how we can use these techniques to predict and track emulsion stability. So the goal when we create emulsions or any dispersion, a dispersion is a two-phase system. And for the kinds of materials we'll be talking about today, usually the size range of these materials is between 20 nanometers and around 20 microns. These could be either solid and liquid suspensions, or in the case of what we'll discuss today, these are liquid-liquid emulsions. So with emulsions, what we want to do is, as you look over to the right here, this is an emulsion where we have stability, where the droplets are staying in suspension and are remaining at their original size. What we want to avoid is having these grow in size, which is coalescence, and also we're trying to avoid phase separation, which is what you see here, where the oil droplets migrate up to the top and we have a separation of the oil from the liquid phase. When we talk about creating a stable emulsion, we could either talk about an oil and water emulsion, a water and oil emulsion, or some fancier double emulsions. But the emulsions I'll be discussing today are a fairly common one, which is an oil and water emulsion. The drawing you see here to the right is a depiction of an oil and water emulsion. The oil is the dispersed phase, and it is surrounded by the continuous phase, which is the water. But in order to create this as a stable emulsion, what we're going to do is add a surfactant. And what that surfactant is going to do is align in such a way that it helps the oil be more comfortable staying in the water. So the surfactant has these two components, the ionic head, which is hydrophilic, and then the RC, the carbon chain, which is hydrophobic. And what these surfactants do is they align in such a way so that we have the hydrophilic head in the water phase and the hydrophobic tail in the oil phase. And the choice and the concentration of these surfactants is critical in creating stable emulsions. So to create these emulsions, we mix the oil in the water phase, but then we need to add energy to help create these emulsions and to reduce the droplet size. In order to stabilize the emulsion, we need to add a surfactant and sometimes mixtures of surfactants. So let's now look at the properties of these surfactants. And surfactants have two components, the hydrophilic head, which likes being in water, and the hydrophobic tail, which is usually a RC chain, hydrocarbon chain, which is happier in oil. The properties of the hydrophilic head vary, and that's how we categorize different kinds of surfactants. If the hydrophilic head has a positive charge, then that is a cationic surfactant. An anionic surfactant has a negative charge in the head group. If there's no charge in the head group, that is a non-ionic surfactant. And there are actually surfactants that are both positively and negatively charged in the head group, and we call these zwitterionic. The choice of surfactants can be important depending on the kind of sample that we're trying to stabilize. Cationic surfactants are good if the dispersed phase is negatively charged. That way, the cationic head is attracted to the dispersed phase. That's used for a lot of natural products, but it's more expensive and more pH dependent than other kinds of surfactants, so a little trickier to use. Anionic surfactants are good to use if the dispersed phase is positively charged. But in general, I tend to use mostly non-ionic surfactants because usually I don't know much about the charge of the dispersed phase before I start working with them. So I'll usually reach for non-ionic surfactants if I don't know much about the sample before I begin. In zwitterionic surfactants, this is often used in the food and the pharmaceutical industry. And a common example of this would be lecithin, which is used for all kinds of products, especially in the food industry. The surfactants I used in today's study is I chose one anionic surfactant, which you see the chemical diagram for here. This has several names: sodium lauryl sulfate, sodium dodecyl sulfate, or SDS, So the two surfactants I used today, I chose one anionic and also one non-ionic, and that was tween 80. And you see the chemical diagram for tween 80 here. So these are the two surfactants I used in today's study. Now when you're choosing the surfactant to create emulsions, if you have an idea like I knew I was going to take mineral oil and create an oil and water emulsion with mineral water and DI water, it's nice to know something about the surfactant you're going to choose, and an approach to understand what would be the best surfactant choice for a given emulsion are called HLB calculations. HLB stands for hydrophilic lipophilic balance. So this allows us to create values for surfactants, usually of non-ionic surfactants, but we also see values for other types, and allows us to understand a given surfactant will be more soluble in water or in oil, because typically what I like to do is disperse the surfactant in the continuous phase before trying to create the emulsion. The way to calculate these HLB values on your own is to look at the weight percent of the hydrophile over the total and then divide by 5. The divide by 5 just gets it to an easy scale to use. The example I give here for this surfactant, Loreth 4, is you take the molecular weight of the ethoxylate portion, 76, and then the lauryl alcohol portion is 186. And you just take the portion here and divide by the total times 100, and you divide by 5, and you'd see that for this given surfactant it has a value of 9.7. And how would we use that value? Well, here, as we look at a list of surfactants and HLB values, and you know, with the internet out there today, few of us really do these calculations. It's probably easier just to go to tables and look at the HLB value for various surfactants. The table I show here, I show the reference down below, so you could also find this. What you can do is by looking at this table, and then on the graph on the right, I kind of give you some guidelines, is very low HLB numbers means that the surfactant would be hydrophobic, meaning it would be soluble in oil. So if you're going to create a water in oil emulsion, you'd probably take this surfactant and disperse it in the oil phase to begin. But then as we get above HLB numbers or above 6 or so, these surfactants are water dispersible. And these are the surfactants you would use for oil and water emulsions. And this is what I did, is I took two surfactants. I took tween 80, which has a value of about 15. And you'll see that doesn't really say it's a very good surfactant agent. It's more of a solubilizing agent. And then I used sodium lauryl sulfate. Sodium lauryl sulfate has a value of 40. That's very high up here. And the tween 80, which has a number around 15, that's where it is in the range of an emulsifying agent. So tween 80 is both a surfactant and an emulsifying agent. And that means it probably would help create a stable emulsion. But I also wanted to create an unstable emulsion so that I could show the difference between a good and a bad emulsion, and that's why I chose sodium lauryl sulfate with a very high HLB value of 40. That saying is probably not going to be a very good emulsifying agent, and certainly as I discovered it was not a very good emulsifying agent. So your choice of surfactants can begin by knowing what kind of emulsion you're going to create, looking at these HLB values, and then choosing ones in the range that are optimized for the kind of surfactant that you're trying to formulate. These are the two surfactants I used, and this shows the procedure I used to create these emulsions. I used two surfactants, a sodium lauryl sulfate, which is the anionic surfactant, and I used a high concentration and a low concentration of 10 and 2.5 grams dispersed in 100 ml of DI water. The other surfactant I used, which was tween 80, which is a non-ionic surfactant and emulsifier, I used a high and a low concentration of 5 and 1 ml dispersed each in 100 ml of DI water. To create the emulsion, what I did is I took 1 ml of mineral oil and dispersed it in 19 ml of the DI water containing the surfactant. So the way I did this is I added the surfactant first to the water, stirred it for 10 minutes to make sure the surfactant was completely solubilized or dispersed in the water. And I raised both the water temperature and the mineral oil higher because this actually helps create the emulsion and makes it quicker to create the emulsion. In order to add energy to create the emulsion, I used an ultrasonic probe. And an ultrasonic probe isn't necessarily the best way to add energy, but it's the easiest way in the lab. So I added the energy by sonicating for 2 minutes, and then I started studying these emulsions to look at the properties to see what could I learn about creating stable emulsions through these two samples. Now, the direct measurement of stability that I used was the Formulaction Turbiscan, which we have an image of here. And the way the Turbiscan works is here is my sample, and the Turbiscan scans up and down the sample. And it has both a backscatter in a transmission detector. So what we see here is after a certain amount of time, it'll scan again. And what we see are changes at the top and bottom of the sample. See how this is actually a solid in liquid suspension. And as more particles settle to the bottom, what we're going to have is an increase in the backscatter at the bottom and a decrease in the backscatter at the top. And what we're going to do is look at these changes in the backscatter as a function of position, as a function of time. And this is going to give us an indication of the rate of phase separation. In this case, it was the rate of the particles settling to the bottom. Since I was working with an oil emulsion suspension, what I'm going to be looking at is the change as the oil droplets cream or come up to the surface. So the Turbiscan is a direct measurement of stability. The way I set up the Turbiscan is I measured over 15 minutes and I took a measurement every 30 seconds. So this is a fairly quick study because I was just in the lab having some fun. Typically, if you're going to look at emulsion stability, you'll use a much longer time scale. You might use weeks as a time scale to do these studies. But just to kind of show how this operates, I did very short measurements, about every 30 seconds over 15 minutes. I kept the temperature up at about 40 degrees C. In the diagrams you see here, this is for surfactant A, and below is for surfactant B. And for surfactant A, what you see is very fast changes in this backscatter. This is the backscatter detector. And what you see is a tremendous change in the backscatter reading at the top of the sample. And what that is indicating is the oil phase is quickly separating and rising to the surface. And this is showing us how quickly that is happening. For surfactant B, what we see is a small change on the surface of the emulsion. So this is saying this is actually a more stable, a slow phase separation, as opposed to what we saw for surfactant A, which is indicating a very fast phase separation change. So this is showing an unstable emulsion, and this is showing a more stable emulsion. This is the data just from the backscatter, and there's another calculation from the Turbiscan called the Turbiscan Stability Index, or the TSI, which is a summary of all the changes detected. And that's what we're looking at on this graph, is the TSI as a function of time for the 4 samples. We have high concentration of surfactant A, low concentrations of surfactant A, and here's the data for the high and low concentrations of surfactant B. And what we see as a very rapid change in the TSI for the low concentration of A, low A, this is the least stable of the emulsions. A higher concentration of A led to a somewhat more stable, but still an unstable emulsion. But surfactant B is showing very little change over time, and that is indicative of a much more stable emulsion, and therefore a better choice of surfactant. This is a quick way to demonstrate that for the 2 surfactants that I chose, surfactant A was a very poor choice, creating an unstable emulsion, whereas the surfactant B was more stable and certainly created a more stable emulsion as a function of time. So this is the range of stability given these 4 formulations of emulsions. So that was a direct measurement of stability. Now let's look at some other analytical techniques that can help us predict stability. And these will include measuring the droplet size using dynamic light scattering. And DLS works from about 1 nanometer to 10 microns. This is our Nicomp system. So we're going to look at both particle size and zeta potential, the charge on the surface of the droplets. And then we're also going to look at the tails of the distribution. We'll use this technique to look for the mean size of the emulsions. Then we'll use the AccuSizer, which is based on single particle optical sizing. This is the AccuSizer APS. Has a size range of 0.5 to 400 microns, and this is a technique we're going to look at the tails of the distribution. There's a precedent for using this combination of both dynamic light scattering and the AccuSizer SPOS system. And there's actually a USP test. This is a test written in the pharmaceutical industry that says for these lipid emulsions are used to add nutrients to patients in hospitals. The USP 729 test says use 2 techniques to measure the size. Use dynamic light scattering, such as a Nicomp, to measure the mean size. And the mean size to pass this test must be below 0.5 microns or 500 nanometers. And what you see on the right is a Nicomp result for one of these lipid emulsions. And you'll see the mean size here is 313 nanometers, which is 0.3 microns, so this would pass. So there is a precedent for using the Nicomp DLS system to measure the mean size of emulsions. And then there's a second part to this test, which is method 2, which says use the AccuSizer and use this technique to measure the volume weighted percent above 5 microns. And this is proven to be a very consistent indicator of emulsion stability. This calculation is called the PFAT5, and the AccuSizer is the industry standard for measuring this percent above 5 or just above some other size above 1 or 5 microns. If you'd like more information on this test, there is an application note on our website, which you can download to read about USP 729 testing. So that's why we've chosen these two techniques to look at emulsion stability. As we look at the photograph on the left, this is an emulsion that has been fairly stable. These are large droplets here that are easily noticed. This has a PFAT5 down at 0.025%, and this is one that's going to fail where there's actually more of these large droplets showing up. These are scanning electron micrographs, but actually using the AccuSizer is a much easier, quicker way to make these measurements. So here are AccuSizer results for a lipid emulsion that is destabilizing. And you can see as we go from the upper left and to these other results, this percent above 5 microns keeps growing and growing, and this is indicating a rapidly destabilizing emulsion. And looking at this percent above 5 microns is a very quick and easy way to look at the instability of these particular emulsions. So dynamic light scattering is how we're going to measure the mean size. Most people should know, if you're attending this seminar, how DLS works. The particles are moving due to Brownian motion, the image you see up here. From the Brownian motion, we can calculate the translational diffusion coefficient, and then we calculate the radius, the size of the particles, using the Stokes-Einstein equation. Simple measurement, take a sample, collect the light scattering, and get the result. So we're going to use dynamic light scattering to look at the mean diameter of these emulsions. And then we're also going to look at the zeta potential. And the reason we want to look at the zeta potential is because the charge on the surface of particles is another indication of stability. Here are two charged particles, and if we build up the charge on the surface of these particles, or in the case of this study, emulsion droplets, as we increase the charge on the surface, then these particles will start repelling each other like magnets. And if they repel each other, then they never have a chance to join, stick together, coalesce, and when they coalesce is when they're more likely to phase separate. So if we put a charge on the surface of the particles, then it's less likely that they're going to stick together. So down here we see there's no charge and they can actually get close enough to stick together. Put the charge on the surface and these particles can never get close enough to actually start coalescing. Now, depending on the kind of dispersion we're looking at, there's a certain value of zeta potential is required to create stability. And with emulsions, that's the lowest value. Typically with emulsions, as long as we have a zeta potential greater than 10 millivolts, then we are seeing an indication that we should start seeing a more stable dispersion. For solid and liquid dispersions, we see it requires more zeta potential to create these stable dispersions. It doesn't matter if they're positively or negatively charged, it's just the magnitude of the charge on the surface. But as we see on this slide, here's this droplet or particle which is negatively charged, so we see positive ions attracted to the surface of the droplet. Since there are positive ions near the surface of the particle, then negative ions will be attracted to the positive ions, and we call this building up the double layer around the surface of the particles. And the zeta potential that we actually measure is not the charge directly on the surface. What it is out here at this distance from the surface of the droplet, which is called the slipping plane. And here at the slipping plane, this is the distance at which these ions will move or migrate with the droplet. The potential in millivolts at this distance from the surface of the droplet is the zeta potential. And this is this other value, stability, that we're going to use in this study. The way we measure zeta potential is we apply an electric field, and the direction of the motion of the droplet tells us whether it was positively or negatively charged. And then we measure the speed of the droplet, and that tells us something about the magnitude of the charge. So we need to apply this electric field, and then we're going to measure the motion of the particle, and from that we're going to calculate the zeta potential. When we understand the zeta potential on the surface of the particles, that is an indication of stability. This is a result which I actually have in another application note you can find on the website on dispersion stability. This is zinc oxide. What you see here is where we have a zeta potential that is very low at 0.7 millivolts. We're actually starting to see, here's the primary particle, then we start seeing aggregation. Whereas when I measured the sample and I had brought the pH up to 9, where I had a zeta potential of minus 31 millivolts, we have just the primary particles and no aggregates. So we're often interested in what surface chemistry properties create a higher zeta potential to create a more stable dispersion. So zeta potential is used for all kinds of samples to measure stability. I'm showing on this slide just the settings I used for the measurements with the Nicomp for these emulsion samples. On the left I show the settings I used for measuring the particle size. Fairly standard settings where I basically left most things to automatic. On the right side I show the settings I used for zeta potential. I used our dip cell, which I will show you an image of in a moment. I applied an electric field of 4 volts per centimeter, used the Shmolakowski equation to calculate the final value. And we used phase analysis to do the zeta potential measurement. So here's a short video, if this plays right for me, where I'm just pipetting the sample into a disposable cell. I then take the electrodes of the dip cell and place it into that cell, cleaned off any water that might be on the surface, attach a cable, and then drop it into the system for doing the measurement. From that point, it's just about another 60 seconds or so to get the zeta potential result. Now I really like the dip cell because this allows us to use a lower electric field strength, which reduces Joule heating, which is easier on the sample, but also reduces a random motion because there is also some Brownian motion during the sample. So I really like the dip cell approach for doing these kinds of measurements. And I just show in a table over here kind of the electrode spacing and the electric field strength I use for most kinds of samples. So this is a brief overview of how to do the zeta potential measurements. There is a YouTube presentation you could watch on doing these measurements if you visit our YouTube channel. Here are the results for both the mean size and the zeta potential of the 4 samples we have: high and low concentration of surfactant A, high and low concentration of surfactant B. And as you look at these sizes, all of these are below the 500 nanometer limit, which in USP 729 says an indication of we've created decent emulsions. This polydispersity index is a calculation of the width of the distribution, and in general, smaller sizes will be more stable than larger sizes, and more narrow distributions are generally more stable than very broad distributions. Then what we see in the final column is the zeta potential. What we see is as we add more surfactant, we achieve a higher zeta potential, which is typically indicative of being more stable, but we're already way above that 10 millivolts that I'd indicated was required to say we have a good formulation of an emulsion. So these values weren't terribly helpful in trying to determine the optimum conditions for emulsification. But higher concentration leads to higher zeta potential. And this alone doesn't tell us about formulation stability. That's why we covered this concept of HLB calculations, which is another indication of how to choose the best emulsions for a given kind of emulsion. Now, what you see here is one of these results. This is the result for low concentration of surfactant A. And you'll see how this is actually, with dynamic light scattering, this is always a fitted result. This is a Gaussian result. It indicates there's nothing greater than 2,000 nanometers as 2 microns, and actually there are. So dynamic light scattering is excellent for showing us the mean size of these emulsions, but it's not really giving us enough information about the tails, and that's why we're going to use the second technique, which is the AccuSizer, to look into the tails of the distribution, which are another excellent indicator of emulsion stability. And for this sample, I'll show you there really were particles larger than 2 microns. So the AccuSizer is based on the technique of single particle optical sizing. We count and size the particles one at a time as they pass through the sensor. As they pass through the sensor, we have 2 detectors, a scattering detector and an extinction detector. We sum these 2 pulses, bring that into the counter, which is a pulse height analyzer, and through the use of a calibration curve, one at a time, we count and size the particles. This is a very high resolution technique, and that's why it's so sensitive to the tails of these distributions of emulsions. So the AccuSizer consists of this sensor, which we see here, the counter, which is a pulse height analyzer, and we need a sampler or fluidics to bring the sample through the sensor, but also often to dilute the sample, so there's only 1 particle at a time passing through the sensor, and that is to avoid coincidence. If 2 particles were present in the sensor at the same time, we'd size and count those 2 particles as 1 larger particle. That's called a coincidence error. So especially for emulsions, which are fairly high concentrations, we need some way to reduce the concentration of the sample before we take the measurement. And for this particular experiment, what I used was the AccuSizer APS, a small picture of it here. And here is a diagram of how the fluidics work. So this is the technique we use when we're measuring high concentration samples because it's a two-stage dilution system. We take the sample into the sample loop. And this is loop volume VL, the loop volume. And then what we're going to do is transfer this into a dilution chamber which has V2, which is our first dilution step. So we know the volume of the loop, we know the volume of the chamber, and this gives us our first dilution factor, V1 over VL. Now what we're going to do is take the sample which has been diluted in this chamber and pump it down through the sensor. But before it reaches that sensor, we're going to bring in another line of filtered water. And here we're going to look at flow rates, and what we're going to do is look at the flow rate coming from this chamber divided by the flow rate coming from here, and this is going to give us our second dilution factor. So we have control of this loop volume, we have control of our flow rate of the diluent here, and here we can adjust what we call DF2, and this allows us to dilute the sample even for very high concentration samples. We could talk about doing a dilution factor of like 1,000,000 to 1 if we need to, and very accurately still understand the count and concentration passing through the sensor. So for emulsion samples, we typically use the AccuSizer APS, which is a dual-stage dilution system. This is just showing a screenshot from the software, and these are the conditions I use for the AccuSizer APS for these measurements. And I set the initial dilution factor pretty high, up at 1200, and let it dilute down from there, down to below a concentration of 4,500 particles per ml before we started the measurements. So just the technical part of how we set up the experiment to do these measurements. And now let's start looking at the data generated by the AccuSizer APS. So this is particle size on the x-axis going from 0.5 microns up to 5, and this is relative volume percent. And what you see is there are more particles out here, especially at this size range, for low concentration sample A. So in general, what we'd want to have is as few particles, few large particles as possible to create a stable emulsion. And what we see is there are larger particles for surfactant A, and then this is low A and high A. And these two results are high and low concentration for surfactant B. And the initial indication from the AccuSizer says low A was our worst emulsion, followed by high A, and then high and low B. So this perfectly tracks what we saw with the Turbiscan down here. So we get this indication. These measurements are made as soon as I created the emulsion. I made these AccuSizer measurements, and it completely tracked what we then saw with the Turbiscan, which is a direct measurement of stability. So one of the advantages of the AccuSizer is you immediately get an indication of stability right when the emulsion is first created, as opposed to some of these other stability tests take quite a while. So the percentage, I don't see anything yet greater than 5 microns. Maybe for this sample would say, what's the percentage greater than 1 micron? And if we looked at the volume percent greater than 1 micron, the data from the AccuSizer would match up completely with the data generated by the Turbiscan. So this data was taken as soon as I created the emulsion. The next thing I did is I waited 5 minutes, and I took a measurement, so we had the T equals 0 right when I created the emulsion, and then with emulsion A, I waited 5 minutes, and look at what happens after 5 minutes. All of a sudden we start seeing these droplets up at 5 microns. And that is the indicator used in USP 729 for emulsion stability. So emulsion A destabilized very quickly. Maybe you would use greater than 1 micron rather than greater than 5 microns for the sample, but the AccuSizer is an excellent indicator of stability both at time t equals 0 and as a function of time. Down below we look at the result from t equals 0 and t equals 5 minutes after I created it for emulsion B. And we see this increase in the number of particles greater than 1 micron, but not as fast as the increase in emulsion A. The AccuSizer is an excellent indicator of emulsion stability. Now there are a lot of droplets down below 0.5 microns. Remember, the mean size is down here at 0.2 microns. And that's why we use two techniques, the dynamic light scattering system, the Nicomp, to look for mean size, and the AccuSizer for this sensitivity to tails. And using these two techniques, we actually get a very good indication of emulsion stability both at when we first create the emulsion and as a function of time. By the way, if you're doing a lot of formulation, a lot of people I know who do this kind of testing have a very high sample load. We can actually hook up an AutoSampler both to the AccuSizer or to the Nicomp system, which is what you see here. You could load up trays and then just have it automatically run through all these samples if you don't have the time to be working in the lab and manually measuring all these samples. So very easily can integrate the AutoSampler to either the Nicomp or to the AccuSizer. That was a study I wanted to show you today, how we used various techniques for studying formulation stability, both the formulation and for stability testing. We used the Turbiscan as a direct analysis of stability as a function of time. We used the Nicomp DLS system to look at the mean diameter and also the Zeta potential as we created these emulsions. And then we used the AccuSizer APS using single particle optical sizing, looking at the tails, what's the volume percent greater than 1 micron or greater than 5 microns, and that also is an excellent indication of emulsion stability. So this combination of various tools allows a formulator to understand which formulation, what preparation leads to the most stable emulsions. So if you want to look at the other technical documents, the other application notes I mentioned during this presentation, please go to our website. The URL is here. And if you go to Documents and go to the Documentation Download Center, you could download these other application notes to get more details on these other tests. I hope that this was helpful.